So today I'm going to be talking about some work I did in the SAVAK group, a very similar story to what you just saw, but for a slightly different system. So here we're once again looking at multidimensional control, but now for a more direct barrier crossing here. So the video that I'm showing right here just shows two different types of protocols. One is the naive, that's exactly the same as what Miranda just described to you before, where you just linearly drive between your two endpoints. The other one is this designed protocol, which is designed in a very similar way to what Miranda just showed to you. And basically, I'm going to describe the principles for how does this design protocol, once again, minimize the excess work, and what properties does it have, and what things can we learn from this. So I'm going to start with a little bit of motivation. And in particular, for this model system, we're going to be thinking about DNA hairpin folding and unfolding experiments. So you can imagine a system such as this, where you have a micron-sized bead, which you can see through your microscope, for example, trapped by optical tweezers. And this example I'm showing here from Woodside is dual trap optical tweezers. And then between them, you have some sort of polymer or DNA linkers attached to a DNA or RNA hairpin. And then by changing the center of these lasers, you can pull apart this DNA hairpin, pulling apart these bonds, and causing conformational change from the folded to unfolded state. And then an additional parameter that you can change is the intensity of the laser, which you can use to then vary the stiffness of the trap as well. Now, a couple things to note about this, which will be important for modeling, is if you look at these free energies here, you notice that the energy scale for these transitions is typically on the order of like 4 to 16 kT. And then in terms of length scales, we're looking at from the folded to unfolded state, basically on the order of like tens to hundreds of nanometers typically. Okay, so this brings us into the modeling. So like we've seen a few times, this is a stochastic system. So here is just a Langevin simulation where the ball represents the micron-sized bead. The gray is the energy landscape imposed by the DNA hairpin, for example. The red is your optical trap, represented by a harmonic trapping potential. And then green is just the total potential. So as you pull it from the folded to unfolded state, for example, essentially, each time you do this, you're going to have different amounts of work. But then when you do it many, many times, you can average this out, and it will follow a trajectory that looks like this. So these bars here will denote one standard deviation to either side of the mean, which is shown as the blue dot. So just a bit of details. Here's my molecular energy landscape. We have some barrier height EB, some distance from the minimum to the peak, which is XM, and then we have the position X. And then we have our harmonic trapping potential, where we're going to assume that we can control both the stiffness and the center of the trap, which is denoted by K of T, and X with a subscript C denoting the center of the trap. Okay, so that's the model that we're going to be looking at. In this system, there's basically two important kinds of work that you do. And these, I think, are quite intuitive when you look at them in this way. So when you move the center of the trap, the type of work that you do is a lot like the familiar force distance work that you think of typically. So as you pull this trap, the bead will lag behind it, and then based on the distance that it lags behind, you're going to have this linear restoring force. So the work that you do from this type of control is very similar to just like the force distance work that you're familiar with. Okay, and then the other parameter that we have is the stiffness. And this one can be a bit more confusing, but I think it's best to think of this kind of like a pressure volume work. Really, these are more like inverse pressures and inverse volumes, but it's nice to think about it this way. So the particle, which is fluctuating around, exerts a pressure outwards. So if you look at on average, the standard deviation exerts an outwards pressure. Then as you tighten the trap, you're constraining it to a tighter and tighter volume. So in this way, this is sort of like a pressure volume work that you'd be familiar with thermodynamically. Okay, so just like we saw in the previous talk, our goal is going to be to perform this task of doing this barrier crossing at minimum work. So basically, we're going to want to minimize the contributions from these two different types of work. And we're going to do it in much the same way as what you just saw. Okay, so I'm going to spare you the details, since you've seen the similar calculation already, of how we calculate the friction and these optimal protocols. I'm going to go more specifically looking at the properties of these protocols. So I have several curves up here. Let's see if I can get this. All right, so I have a few curves up here. So this one is the naive protocol that you just saw before. So this just starts at the beginning with the trap in the left well. and then you drive it as a function of time linearly without changing the stiffness from the left well to the right well. Okay, and then this curve here, this dashed dotted line is the median position of the particle. And then these different shaded regions are given by the quantiles. And if it was a Gaussian distribution, then these quantiles would be evenly spaced. So this is the naive protocol, which just linearly drives it. This is this 1D linear response, or 1D optimized. This is similar to what you saw before, where we just do this time optimization. So it still goes from the left well to the right well. And you can't actually see it in this type of curve, but it slows down in this region as it goes over the barrier and then speeds up at the ends. Okay, but really the one I wanted to focus on here are the next two. So this is the two-dimensional control, where we have control not only over the trap center, but over the trap stiffness. So if you just look at the potentials here, we again start in the left well, but then when you go over the barrier, rather than having this bistable potential here, you tighten the trap, creating a monostable potential. And then at the end, you once again end at the same position. And the nice thing about this protocol is if you look at the distribution, what you find is that these quantiles are linearly driven between the two endpoints. Now it turns out this is a known property of some of optimal transport theory, so it's got some nice connections there. And essentially, by doing this tightening at the middle, you avoid this region in the middle where your standard deviation or your variance becomes a lot wider. And then the other interesting property is if you compare this to the 1D linear response, it actually makes it a lot further on median than the 2D linear response makes a lot further than the 1D linear response, and the naive that barely make it over the barrier. Okay, and then there's one final protocol here. So all this theory that I presented, that Miranda presented before, is for slow protocols. Now it turns out I did some work with Miranda on fast protocols, and it turns out this is optimal when you go very slow, but it turns out when you go very fast, rather than doing a continuous protocol, the optimal way to drive the system is to do discrete jumps. So basically we have what we call the interpolated protocol, which kind of combines these two ideas. Basically, as you go faster and faster, you'll get bigger and bigger jumps. And by jump, I mean at the beginning, rather than starting from this purple, you jump to this green curve here. And at the end, you have a jump. So the jumps will get bigger and bigger the faster and faster you go, and they'll get smaller and smaller the slower and slower you go. So these are the general properties of these design protocols. And here is the naive and the interpolated shown here once again. And if you look at, for example, the standard deviation here, you see the large spread in the distribution, whereas this one does not have a large spread in the distribution. Okay, so here is just once again saying all these different properties. Here's if you don't like videos as much, we got as a function of time, the trap center, and the stiffness for all these different protocols. Main properties are that it slows down at the barrier. It tightens when you cross the barrier. So if you look at, so here are these trap center, see all of these curves have a shallower slope. So they're slowing down over here, and then they speed up towards the end. And then this green one has these jumps once again at the beginning and the end. And then for the stiffness, if you look at this 2D linear response or the interpolated here, you'll find that these curves have a much higher stiffness in the middle, and that's where it's crossing this barrier. Okay, and then these allow it to linearly move the mean and roughly maintain constant variance. Okay, and I would like to just end off with showing just how well these protocols actually perform. So in particular, this is this excess work quantity that we've seen before, and these are several different protocols. And on the horizontal axis, we have the protocol duration scaled by some relaxation time of the system. Okay, so over here will correspond to very slow, and over here will correspond to very fast. Now to answer this question that we had before of comparing different levels of control, we can look at them on this diagram here. So this naive, this is not optimized at all. And then when you have this one-dimensional optimization, it goes down very slightly. But then once you add the stiffness, you have a very large decrease in this excess work going all the way down to here. In particular, these blue and these green ones. Okay, and then we can look at the fast limit. As you go faster and faster, it turns out this slow approximation breaks down and doesn't perform very well. So we have this interpolated protocol, which you can see does quite well, even as you go faster and faster. Okay, and then for comparison, to answer this question about comparing different levels of control, if you had infinite control over your system, so full control over the potential, you would achieve this, this sort of magenta curve here, which you can see already with two-dimensional control. We line up quite well with that. And the reason for this is basically because our system is approximately Gaussian. Basically, you just need two parameters to control that system, the mean and the variance. Okay, and then this is just another way of looking at the dissipation. And with that, I would like to thank you and welcome any questions.